I guess there's all this talk about like agentic coding with very fast codex, right? Like as Sam Altman put it. But do they have a way to handle long context storage with this whole Cerebras system?
Welcome to another Semi-Doped podcast. I'm Austin Lyons of Chipstrat, and with me is Vic Shaker from Vic's newsletter. Hey, what's up, Vic?
Hey Austin, how's it going?
It's going well,
I
man.
shouldn't call you Austin. I guess you're now Tom. Did you did you see on Twitter how somebody said you look like Tom Holland? They're like,
Yes.
wait, why is Tom Holland speaking semiconductor stuff? Like, what's going on? Like, is everybody an AI head now? And then I looked up Tom Holland. I'm like, holy shit, you look like him. That's awesome.
I've never gotten that. I too had to look him up, and I was like, oh yeah, it's the Spider-Man guy. Cool, I'll take it. I haven't gotten it, but famous movie star. I'm sure he's like 10 years younger than me, so let's go.
All right, your friendly neighborhood Spider-Man talking to you semi stuff today. Yeah,
I like it.
yeah,
Yes, I need a
let's do
T-shirt.
it.
All right, so Vic, you wrote a post about context memory storage, and I learned a ton. It was really good, very in depth, and I actually liked. You had a lot of really cool illustrations. But let's start there with our audience. Why don't you take it from the top? Like, what should we know about context memory storage?
Yeah, so the whole thing got started because Nvidia at CES mentioned inference context memory storage. We mentioned it in our podcast about Nvidia CES also. And the whole thing is all about having just a bunch of NVMe flash storage in a rack, and then hooking it up with like really fast networking to your main GPUs, and just have it store stuff. And it seems like this idea is not new. You know, people have had these flash disk arrays in a networked storage for a very long time, but the very fact that Jensen mentioned it in this big forum immediately has everybody looking up NAND, and then the prices went up for all these NAND companies. It's the usual thing,
Yeah, the
but
Midas touch.
yeah, the Midas touch, the Jensen touch. Yeah, he does this, and you know everybody talks about this stuff. So I think it's important to talk about it a little bit more than we did last time, because it unlocks a whole new era of things we can do in AI inferencing that just wasn't possible before, right? No, so for anybody who's actually used like these tools, and I'm guessing it's a lot of people at this point, you know, I in Claude especially, the more I keep talking to Claude, especially in the Opus mode, which consumes a lot more tokens, pretty soon it says like, that's it. This chat is now run out of like full. It's full, or you're done with this chat. Continue your conversation in a new chat. You know, if you ever see that, um, or more recently, it has started saying, "Hold on, I'm just compressing our chat so we can continue talking." So what is actually happening behind that is the context memory is filling up. Like there are only so many tokens that can be stored, and after some time something has to be done with those tokens to continue the conversation, right? Or they have to be discarded, in which case, you know, AI forgets the entire conversation you've been having with it all this time, which is extremely frustrating, because now you're like, so what do I have to tell you all that stuff? I just told you all this stuff, now you want me to say all that stuff again? It's terrible, right? So then you copy your original prompt and begin. It's very frustrating. uh, so the compacting idea was good, except that in my own usage of Claude, for example, it kind of forgets stuff. It gets amnesia, and it's like tells me stuff that I've already told it before, and it's like, did you forget that, or or, or it tells me something I never said to it before. Anyway, it's just messy,
Mm.
and all of this is because context is running out. Okay, so what this context memory storage solves is exactly that. uh, you can actually have really long conversations if you can store more context, right? And this is getting more and more important, especially when we are in the age of agentic AI and agentic workloads, especially like AI based coding. You know, there was like a piece of news 2 weeks ago where the Cursor CEO said that they built an entire web browser just with like ChatGPT 5.2. They just like prompted it and then let it run for like a whole week.
Wow,
It came up with a browser. It's kind of fantastic.
this is wild.
Yeah, it used to take like a couple of years before, and a whole team of people building browsers, right? You didn't see browsers come out every day. Like when Chrome came out, that was like a big deal. And then before that was, I don't even, like you and I probably remember Netscape Navigator. Like, that was like way before even Internet Explorer. So you don't have browsers coming out every day. But if AI can make a whole browser with all the support possible in like a week, that's fantastic. Now, what does it take to run a whole AI job for a week to do something like this? This is the kind of stuff that context memory unlocks.
Mm. Because it takes lots and lots of tokens. It probably has like a big code base that it's generating. And at the end of the day, it can't store all this in HBM, right? So it needs to store this context somewhere.
Yes, we should talk about unpack that a little bit, right? So tokens are our currency of AI in a sense, because all the words we put into the chat box on LLMs are converted to numbers, and that process, you know, the resulting number is called a token. It's kind of broken up in some way. Now, the question is, what does it mean that we're running out of uh, we can't store tokens? What does that even mean? Like, are we storing everything? Like, there is some nuance to what it is that we exactly have to store, right? So one of the big things that is a selling point for a lot of LLMs is the context window. So when you see like Gemini has a 1 million token context window, what that means is that it can take 1 million tokens together and form relationships between all those tokens. So it knows the first token and the millionth token and the relationship between them. So that is what we want to do. Now, in the process of generating output tokens from the input tokens we give it through our prompt, there's like a whole bunch of calculations that happen here. And this is essentially what the LLM transformer is doing. And within that functionality is something called attention. Like, this is the fundamental revolutionary concept that Google introduced in their 2017 paper, saying attention is all you need. Attention is a mathematical formula. Uh, and the whole idea is that you calculate a bunch of matrices, right? So it involves a bunch of matrices called the key and the value and the query matrix. And then, of course, there are the weight matrices. Now, for every token that comes in, there is a key value cache, there is a key and value pair that is calculated based on the model weights. So the model weights are what has been the model weights are basically what you get from training. And using an input token, you can make a key value pair, and that is stored in memory. Then the next token comes by, you make another key value pair, and you add it to the first one. And you keep, for every input token, you keep adding key value pairs to this original matrix. And so as the context length grows, your key value matrix grows linearly with it. It's not a quadratic or cubic or anything. It's a linear increase of the KV matrix. And that is what is called the KV cache. This KV cache has to be stored somewhere. Now imagine if you have 100 million token input window or 1 billion tokens. I don't know how many agents would need. If you have 1 billion token window, you need to have a massive KV cache stored somewhere, and it can't be in HBM. So this is where we land at what you said. We don't just have enough HBM for this.
Mm.
Right?
Makes sense. Yes. So, okay, we calculate all this key value pairs as part of the attention, paying attention to all the different words and the relationships between them. And the longer the context we have, like the more useful the AI is, because we're giving it all this reference information, PDFs, all, whatever, what have you, code bases, entire code bases. But at some point, there's too much, and this can't all fit on the HBM on the GPUs. So where does it go?
So HBM is on the Rubin is 288 GB. Okay, half of that is taken up by the model weights. Let's say it depends on the model, and so let's say you're left with like I don't know 150 GB of HBM. That's not enough to store 100 billion tokens. It doesn't matter how small you make it. People have thought about ways like with multi-headed latent attention and grouped query attention. Smart people have come up with very smart ways to reduce the size of the key value cache you can store, but you just can't store everything in HBM. So what happens next is that whatever spills over from HBM is stored in the CPU DRAM. So we mentioned in the CES episode that the Vera Rubin platform supports 1 to 1.5 TB, depending on what kind of RAM sticks you throw in there, of DRAM in the CPU. That is also intentionally designed for longer context storage because in the Blackwell series, you only had 480 GB of DRAM associated with the Grace CPU. In the Vera CPU, you have over 1 terabyte. So you can store a lot more context on this. So whatever spills over from HBM goes to DRAM. And DRAM is good. It's not as good as HBM. It's still pretty fast. So you can get this back pretty quickly when you need it. Now, if it doesn't fit on DRAM of the on the CPU, it goes out to the next level of storage, which is maybe the local SSD. The local SSD is all good, but when you're serving 100 million people, all of whom are running agentic AI workloads, that is not going to fit on a local SSD. So now you have to go at scale. You need petabytes of storage in a rack server somewhere, and that is where all your KV cache is stored.
Gotcha. So we're talking about memory hierarchies here.
Yes, totally. And just like any other memory hierarchy, right, you have a latency and a throughput associated with each one. HBM is the fastest. So if you can get your KV cache quickly when you need it, that's very good because you can compute your output token quickly. And then you have a very low time to first token and a high throughput of tokens because you can keep getting KV cache quickly. Now, the farther down this memory hierarchy you go, all the way to like network storage, this gets pretty difficult to do quickly. And the time to first token and all of those metrics throughput drops. Now, there are ways that things have people like Weka with their augmented memory grid, or even the ICMS system, the context memory storage system that Nvidia is planning. They're all finding ways to make this access of this data from this large storage pool really quick. And that is where it all lies. Like, so you have to be able to store a lot of information, but also get it quickly.
Mm-hmm. Yes. So this reminds me, if anyone has studied CPUs and like L1, L2, L3 cache, there's like that nice pyramid where at the top it's SRAM and it's like the smallest and it's the fastest, but it's the most expensive. And then you go down a layer and it's bigger and it's cheaper, but it takes longer to access. And you go down further all the way, SRAM through DRAM all the way down to SSDs and even like cold storage. I saw that Nvidia put out a diagram very similar. Instead of L1, L2, L3, they called it like G1, G2, G3, probably for GPUs. Same concept. There's always a trade-off, more storage and cheaper, but it's slower to access. Now, I thought it was interesting that they put G1 was HBM when technically maybe there's a G0, which is SRAM. And I just say that because, of course, they're only, in NVIDIA GPUs, the SRAM is for like local computations like registers. But of course, there's other AI accelerators who are using SRAM to actually store the weights in the activations and presumably the KV cache as well. But anyway, I just thought it was interesting. But carrying on, so you're talking about essentially Weka, NVIDIA, others are trying to ask, how can we take like that lower tier of storage on the pyramid and have the benefits of cost and capacity, but speed it up? So kind of almost like move it up the pyramid a little bit. Or you have a nice diagram where you showed this as well. So talk a little bit more about how to like get the benefits of the storage, but trying to speed it up so it acts as if it was like a level higher.
So they're just these data processing units that really reduce the latency and increase the throughput from all these storage devices directly to the GPU. So you can take a lot of information and bypass all the middlemen, or so to speak, like PCIe controllers and all these network switches, and then directly take it straight to the GPU using something called GPU direct storage. Yeah, so GDS. So you can just like move large amounts of data, and this will help get it to the destination quicker. So they're making some modifications to the whole process to make sure that GPUs get the information they need.
Nice. So tell me about the benefit of this with regards to tokenomics.
Yeah, so I was looking this up recently. If you look at like Claude and go into their API docs and look at how they charge for tokens, they have a they have a token system based on where the token is in the inference process, and so to speak. So for so many input tokens, you have a certain price. I think it's like, I don't know, like let's say $10 for million tokens or something like that. And then for output tokens, it's actually much more. It's more like $25 per million tokens. And then for cache hits, you have something like $5 per million tokens. So what that means is you're looking for that KV cache, but if you have a cache hit uh, or a cache miss, it charges you differently. So if you want to write it to cache, you have to pay a certain amount for a million tokens. So for example, if you want to write a million tokens to cache and hold it there for like 5 minutes, it's probably going to cost you like $5. Okay, these numbers are not exact. I don't, but it's on the API. You can check it out, and they change too all the time. So uh, if you want to hold the same tokens for like, I don't know, let's say an hour instead of 5 minutes, it costs more. So you have to kind of plan what kind of tokens you want to keep in cache and for how long. This arbitrage is very important for you to keep the cost of inferencing down. Now, I mentioned about the cache hit versus cache miss. So you've made some decisions on what you want to store in the cache and for how long, right? If you are right about that and you hit the cache and it's a hit, then your cost of inferencing is 1/10 what it would be if it's a cache miss.
It makes a ton of sense. It feels super complicated to expose this in your pricing to say, like, think about what you're storing in a cache. And if you get a cache hit, it's way cheaper. But if you get a miss, it's way more expensive. On the other hand, and I'll let you carry on, but I just want to point out it goes to show that clearly this adds up.
Now imagine now you have this massive petabyte scale storage system where you can just store tokens infinitely. Now, I feel personally, and this is what I write about in my rather detailed article on Substack, is that I think that the cache economics of storing caches is going to get much cheaper. You can literally store an infinite amount, which makes it, I guess, infinitely cheaper to store that many cache tokens, right? Think about the fact that you have so much cash now that you can store rather cheaply, and what that does for long agentic coding, like I described. The Cursor CEO said, how he developed this whole web browser in a week. That requires a lot of cash, I would imagine. So, anyway, so what do you think about all this agentic coding stuff?
Yeah, so I think agentic coding is super powerful. I'm trying out Claude Code myself, and I was even starting to talk to my children about it, showing my middle school son, like, dude, you got to check this out. You got to play with this. Anyway, of course, I use Claude Code. I also am a heavy ChatGPT user, and I saw that Sam Altman had tweeted that OpenAI wants to speed up Codex, which is its agentic coding platform. And specifically, how they plan to do that is with a partnership with Cerebras. And so this was super interesting. I clicked on, I was like, what is all this? And I clicked on it, and there was an announcement between Cerebras and OpenAI that OpenAI is partnering with Cerebras to add 750 megawatts of ultra low latency AI compute to their platform. And so, of course, this is really cool. Now, we'll talk about Cerebras. For those of you who don't know, they are an AI accelerator company. I call them a pre-GPT company, which means they designed their chips before GPT exploded in popularity, which means they made design trade-offs before we realized, like, oh, wow, we need huge models in memory, and we need huge context in memory too, right? So this would be similar to the conversation that we had with Grok. They're another pre-GPT company.
Why? I have a question about Cerebras. Why did they make a whole wafer scale engine? Basically, they decided to make a single chip on a whole wafer. Why did they do this before GPT? What was the need for this level of compute?
That's a good question, and we should have them on to have them talk about it. But I think at the highest level, I think they weren't necessarily. The way it comes off to me is that they were not necessarily starting with a problem to solve as much as they were thinking as engineers around constraints and tackling problems from first principles in a different order. So let me explain. So, today we have these wafers, and you can only make each die so big. It's the reticle limit. It's like the window that the lithography machine uses to pattern silicon. And if you want to have even more compute in a chip, you actually start taking these reticle sized chips and then you try to package them together. So this is what Nvidia does with their GPUs. They have like two, big reticle sized dies. They package it together. And then now if you think about Nvidia, you put those on a board and you put a CPU on a board, and then that's your board. You've got two GPUs and a CPU. And of course, that's not enough compute. It's not enough HBM like we've been talking about. And so you scale this up by having more boards in a server node, and then having more servers in a rack, and then connecting all these racks. And so to get, massive compute for AI, for inference or for training, you have all of these. You started with a single wafer, and you make all these dies, but then you chop them all up and then you package them, separate them. But then at the end of the day, you connect them all again. You have all this networking and all these switches and, all these racks. And so if you zoom way out and stop and think, it's like the approach Cerebras was taking was like, why cut the dies up? Why not just have it be one monolithic, like the extent of what monolithic silicon die could be, which is the entire wafer. And what if you just pattern a bunch of die there and connect them all? No SerDes, no cables, no switches, but just like wires on the silicon, if you will, just metal traces, short distance. Wouldn't the data never has to leave the chip to HBM, by the way, if they just use like 44 gigs of SRAM on their wafer in the wafer-scale engine 3. Why not just have all the compute, all the memory co-located? Wouldn't that be way lower power, higher memory bandwidth, higher throughput? So I have a feeling, and we should ask them about their original intentions, that they were looking at where AI was going even before large language models, because there was still lots of AI, right? Like timelines, ranking, that kind of thing, and saying ultimately more compute is always better. And what if we fundamentally turned this on its head and said, how much compute can you actually put on a wafer?
Yeah, that's fascinating. I like the how you just like mentioned 44 gigs of SRAM and just like continued talking about it. That's actually a fascinating amount of SRAM, right? Because all this Grok conversation with Nvidia, like each chip had 230 megabytes of it, right? And this here you have this Cerebras wafer that is 12 inches. Looks like Captain America shield, that's Jensen's wielding all the time. It looks
That's
like
right.
that. It's not that. But yeah, and you have 44 GB of SRAM. That is extremely fast bandwidth. And what does it take to have a Llama 70B model? How many of these Cerebras wafers do you need then?
Yeah, they needed 4 because you have to. You're going to store more than just the weights. You'll store quantized weights, but you want to also have room to store the activations, and then of course the KV cache. But yes, for Cerebras, they could run a 70B Llama on just 4 of their systems, which would be 4 big wafers.
Awesome. All right. Now that we've set the tone of Cerebras, how does this tie in back to like OpenAI, and why is this whole thing with them?
Yes. Okay. So OpenAI had an announcement, and it was Sachin Khatti, who was recently the CTO and AI officer at Intel, and he's also an adjunct professor at Stanford. And I think within the last 3 months, he moved over to OpenAI, and he specifically said that the partnership with Cerebras was about OpenAI's compute strategy to build a resilient portfolio that matches the right systems to the right workloads. And this was like music to my ears. This is something I've been talking about at ChipStrat, which is the idea of having heterogeneous or heterogeneous, I'm not sure how you say the word, compute in your AI accelerator portfolio. Yes, GPUs are flexible and can do every workload, but when you're at such massive scale, wouldn't it make sense to have particular inference clusters really hyper-tuned to your specific workload? And low latency is the first workload where people saw, oh, interesting, these pre-GPT accelerators like Grok, we talked about this with Grok and Nvidia, can actually do way faster time to first token and end-to-end response time for certain small model, sort of low context workloads. So again, it's like a 70B model or something. And if you have those particular workloads, why take the same compute, which you could save for doing something like deep research or video generation or something really computationally expensive that needs a huge amount of context and really high, bandwidth storage? Why don't you save that for that like frontier compute for training or for those inference workloads? And why not have certain systems that are perfectly tailored just for those particular, really fast, really low latency workloads? And so, interestingly, Sachin is coming in and he's saying, yeah, that's what we're going to do. We're going to partner with Cerebras, and they're going to cover this area of our portfolio of workloads. We're going to use their SKU essentially for this ultra low latency, I believe was the word that he used, workloads. And what's very interesting is actually when he was at Intel and I was at OCP, back in October, so just 3 or 4 months ago, Sachin had a keynote where he talked on behalf of Intel about a very similar concept, where he said, at Intel, we're now going to take a workload-driven approach. And so for agentic AI, he pointed out how each step in the workload has different constraints. You've got pre-fill, where it's compute bound, and you actually would be fine with like cheaper memory, not instead of HBM, like LPDDR, because you're not moving things in and out of memory so much as you're just compute bound. You're just needing to crank through and get a ton of flops going. And to that end, actually, Intel introduced Crescent Island. So this idea of an inference optimized GPU for prefill. So think similar to like Rubin CPX. So it was interesting to see that Intel was starting to bet on that same future of what if companies at scale actually optimize their infrastructure for different tasks and even different sort of subtasks in a workload. So going back to Cerebras, he's obviously at OpenAI, and back to their partnership, that was the announcement, was OpenAI wants to leverage some of this hyperspeed compute, if you will. Then Sam Altman retweeted it, and he said, hey, Codex is going to get a lot faster. Check it out. We're partnering with Cerebras, and we're going to speed up coding.
So we have 44 GB of SRAM and some really fast inferencing solutions. And we have also this disaggregated prefill and decode systems that Intel has in their Crescent Island platform, right? So we have all these different platforms that do different kinds of workloads depending on the application. I think that is the key takeaway here, is that there is no real one size fits all, especially when it comes to inferencing, because there are so many demands. Like you could have accuracy as one of the dimensions. You could have time to first token, or latency, if you want to put it that way, as another dimension. So I don't. What are the dimensions do you think of? I remember in one of your articles you had this like really nice radar plot, which I always now use to visualize what workload should look like. Do you remember what the dimensions you had in that plot were?
I should have pulled it up, but yes, it was definitely like accuracy, interactivity,
Yes.
and then like context length and
Yes.
and quantization, and ultimately at the end of the day you can sort of think of it as intelligence too. Like is this a very large model that's really intelligent, or is it just like a small model, not as smart but good enough?
That's great. Like, so one of the dimensions obviously is context length, which goes back to our original conversation about, context storage memory. So I guess there's all this talk about like agentic coding with very fast codecs, right? Like as Sam Altman put it. But do they have a way to handle long context storage with this whole Cerebras system?
So that is the question. Cerebras, if they've got 44 gigs on a wafer and they use 4 wafers to run Llama 70B, that sounds promising. But then you have to ask, oh, where does the KV cache go? And if they want to unlock really long context for developers and they want to offload the KV cache, do they, like, where would they offload it, right? Because they don't even have HBM, it's just that SRAM. Do they have some sort of memory server like Nvidia has announced and like others have? And if you're from Cerebras, come on the pod and educate us. I don't know, but I'll tell you what I learned when I was Googling. So I did see that Cerebras for training has already thought through this, because when you're training, obviously, these days people are training like trillion parameter models. And so Cerebras has built this memory server that's a mix of DRAM and flash, and it offloads all the weights into the memory server, and then it just streams in the weights that are needed at the right time, with a high bandwidth fast interconnect. So I think of it as like streaming in, a particular layer of the network at a time or something. And if you squint, you see, oh, they've got offloaded memory and the ability to stream it in at the right time for the computation. And so I kind of wonder if they could use some of the same technology and use those primitives and build a KV cache management where they could offload KV cache into memory and stream it back in as needed. So my answer is,
Yeah.
I don't know, but I bet they're doing something like this.
Yeah, this question extends in my mind to a lot beyond what it's only Cerebras is doing. Like any SRAM based approach, even if it's Grok, um, would they offload from SRAM because it's so limited? Would they offload to HBM first? And
Hmm.
in that case, is it any different from GPU? Because you have the Grok LPU approach, but now you offload to HBM. So, like you said, the SRAM is a G0 tier, right? Which I don't know, but like Nvidia didn't put it in their diagram of memory storage for GPUs. So I wonder if all these SRAM based inferencing companies just are working in the G0 tier for a very specific application. And when they start offloading to other tiers, I wonder what level of advantage the ASIC based approach has over general purpose GPUs. You know
Hmm.
what I mean? I don't think
Totally.
I understand the answer entirely, but if anybody knows the answer, get in touch with us. We'll figure out a way to learn from you.
Yes, yes. Let me zoom out and give you my thoughts on that. So at the end of the day, there's GPUs, there are pre-GPT AI accelerators, and there's post-GPT AI accelerators. Pre-GPT would be like Cerebras and Grok, and they made certain trade-offs at the time, saying like, yes, we're just going to focus on SRAM, and it's really fast. And now, to your point, as they were made before GPTs, and so they're saying like, with our systems to actually make it work for today's workloads, maybe we have to have this memory offloading. And then to your question, well, what if that's HBM? Doesn't that defeat all the benefits that they had by not having HBM, which is
Yes.
cost, right? And it makes it feel kind of similar in a way to GPUs, which had made different trade-offs of, yeah, we're going to have the HBM right there, right near the die, and it's going to be expensive, but you'll have it there. And now it's sort of feeling like they're almost converging, where it's like they're all using the same components. Now, you've got also, which I'm really excited about, companies like Etched or MADX, who are post GPT AI accelerator companies, which is they know what the workload is. And so from day one, they can design their system for transformer LLM inference, and they can design around KV cache. We haven't gotten many technical answers or demos from them, but it'll be really interesting to see where they land in their memory hierarchy decisions. Because at the end of the day, GPUs are super flexible. They can be used for anything. You can totally use them for LLM inference. There's all these optimizations. You can disaggregate, prefill, and decode using Dynamo. You can have a memory context storage system. You've got all this software. You can take all these tools and put together a cluster that's really tuned for LLM inference. You can take these pre-GPT clusters, try to tune them for LLM inference and on maybe a different vector like low latency. And then soon we'll have these post-GPT AI accelerators. And it'll be fascinating to see the trade-offs across all of them and which workloads they all end up serving at the end of the day.
That's fascinating. Didn't Etched recently raise funds too? I saw that they were in the news.
Yes, totally. They were in the news. It was pretty quiet. Bloomberg, I think, had the scoop that they raised $500 million at, I think, a $5 billion valuation. Etched hasn't publicly said anything themselves yet, so they must be waiting maybe until they have more technical information that they want to share or something. I'm not 100% sure, but what I surmise from such a large fundraise is Etched must have customers, right? If you're raising $500 million, you're building not only chips, but you're building racks, and you must have a hyperscale customer or two lined up, right?
Yeah, I hope you're right. I mean, I don't know. Maybe you don't need all that to raise money these days. Maybe you can just build a concept accelerator. You know why I say that? Because wherever there is compute nowadays, Altman is at that place. Like, if anybody builds an accelerator with any form of compute, Sam Altman's going to come knocking. They're so compute deprived anyway. So
Totally.
I think people will fund it if it's a cool technology.
We should have a venture capitalist on to refute that, or to say, yes, if we, we'll fund it because we think Sam will come play ball. That to that end, when I first saw the Cerebras announcement and it said, we're partnering with Cerebras, they have 750 megawatts of compute. At first I thought, like, oh, is this just a power thing? Like,
yeah,
they're compute limited, they're power limited, and if any startup has both compute and access to power, we're willing to talk.
Yes, I think so, right? I mean, those are the two things that will really drive the availability of compute from anywhere. So
Totally.
It doesn't matter what kind of inferencing solution you have, SRAM, HBM, I don't know, Etched. We'll take it. Can you multiply matrices? Yes. Okay, you're in.
For sure. Now, of course, we won't get into it today, but there are really interesting software questions to get into as well, which is like, oh wow, Sam is signing up his software team to write software that runs on all these different accelerators, AMD, Nvidia, Cerebras, right? How easy or how hard is that these days? So that'll be something fun to circle back to in the future.
Yep.
But for that, I think we are at time. So that's it for today. Thanks for listening. If you're enjoying Semi-Doped, we'd love if you give us a 5-star rating and a quick review in Apple Podcasts, Spotify, or wherever you listen to this. Thanks, everyone, and we'll see you next time.